Thank you very much, Roland, for the kind introduction, and to NNI for the opportunity to talk today about texture and learning to eat. And the title of my talk is Learning to Eat, because unlike many of the other aspects around food and growth, eating is learned. It's not innate. We don't have any innate ability to know how to eat. We are not born with an ability to chew from birth. We have to learn all of these experiences via texture, experiential learning, and the complicated feedback that occurs at a really important period of growth and development in early life. And as I'll show today across a couple of different topics, these behaviors that emerge early in life remain stable and can sometimes also link to the translation between early life risk of obesity and the development of overweight and higher adiposity. So in the next 15 minutes or so, I want to cover three topics more broadly: learning to chew and some of the anatomical developments that occur in the first primarily 24 months of life, and then learning to like, how early life texture experiences both complements the anatomical development but also shapes the food preferences and acceptance behavior that become our dietary pattern in later childhood and ultimately shape our preferred eating styles linked to energy intake. And finally, I'll close with some examples from work we've done in Singapore, in the Growing Up in Singapore to Healthy Outcomes birth cohort, where we had a large piece of work on the development of eating behaviors and links to growth outcomes. So learning to chew. So importantly, we're born with very few innate abilities in terms of preferences or liking or behavior. We're born with an innate preference for sweet foods, but beyond that, everything else has to be acquired and learned at an incredibly complex period of growth and development, where there are many, many changes occurring very rapidly in the first 12 and then also in the first 24 months of life. Much of what I'll talk about today is summarized in a number of review articles that we've written in recent years with my colleague Carole Tournier from INRA. And with Carole, we've focused a lot on the development of oral anatomy and then links to texture experiences and the subsequent emergence of stable eating behaviors. And when we're born, we're really equipped for a liquid diet, for dependent liquid-based feeding in a supine position. We have a very small and narrow palate. We have fat deposits in our cheeks and soft tissues. And this helps to form a strong vacuum in relation to liquid feeding, whether it be breast or bottle feeding, and also helps to prevent the risk of swallowing the tongue and provides additional nutrient sources beyond that first 6 months of age. However, thereafter, as the previous speakers highlighted, we have stronger energy requirements, nutrient requirements that cannot be sustained alone by just liquid feeding. And so we have an elongation of the palate, an elongation of tongue and lips, and a move towards lumpy foods, purees, and then ultimately more challenging food textures. And how does that happen? Well, first and foremost, our palate has to extend to make space for the tongue to move and also for the emergence of deciduous teeth. Our palate length doubles in the first 24 months of life to create this space. And in fact, there's a reciprocal relationship between the act of chewing, more challenging textures, and the extension of the palate. If you chew more and have more exposure to textures, it will also encourage the lengthening of the palate, and the width of the palate will also increase. And as you can see from the graph here, we have significant rises very early in the time in terms of the palate's initial length, and this continues throughout later childhood. And it's quite important because if this is incorrect, of course, it also leads to difficulties with regards to the emergence of teeth. Growth will continue with chronological age, but to support that growth, we have to make space for the emergence of those teeth and space for our tongue to move in a lateral as well as a protrusion movement. And in terms of learning to bite, you'll see that with all young children are keen to put everything in their mouth. They're discovering their near environment through biting, through chewing, in both food and non-food experiences. We've all got the image of a young infant biting pieces of plastic or Lego and just learning the power of their muscles in their jaw, the power of their bite force, and also the kind of force that's required to break food into a manageable bolus, and also what constitutes foods that can be bitten and chewed and foods which cannot. And the initial protrusion reflex that normally pushes pieces of food out of our mouth passes by around the 4 to 6 month period. And this in turn leads to the first emergence of deciduous teeth. We have our first occlusal contacts, and teeth emerge initially around with the incisors, and then subsequently over time, the remainder of the first teeth emerge towards the molars as well. This, of course, coincides with a gradual improvement with muscle coordination, with nerve coordination, and with the ability to contract and relax muscles in a form that can actually close the jaw and lead to formed occlusal contacts to lead for much more efficient chewing. And the functional capacity of the infant increases with every new tooth. As soon as they learn how to use this tooth, it increases the broadness of the textures that are available then to try to learn how to eat more complex and challenging textures. And this coincides also with our thickening and more functional capacity in the masseter and temporalis muscles, the two primary muscles that move the jaw, and also a development of complex fine motor skills, the kind of skills needed to move the tongue in a way that it can move food between molars for more efficient crushing, and the kind of fine motor skills needed to use your lips, where the elongation is matched with the power to close the lips during chewing so that we don't have this oral incontinence often associated with early life, where children who chew food and then it falls out the front of their mouth at the point of swallow. So it's good for chewing, but not great for nutrition in the sense of oral incontinence. 31 muscles and nerves, so 26 pairs of muscles and 5 cranial nerves. All of this has to be learned. Learned at a time when there's no ability to communicate with the child directly in a cognitive sense and give them instructions, learned only through texture experiential learning. And overcoming those kind of challenges initially also broadens the variety that's available in the diet and widens the kinds of textures that can be consumed habitually. These are just some EMG images of muscle activity in the early phase, so tongue muscle and chewing muscles. And you can see that these muscles move in unison and then ultimately result in the hypoid, which is the muscle that's responsible for the swallow action. And simultaneously, the child is learning to coordinate the action of these muscles in response to the textures that they're perceiving in a dynamic sense, because the initial texture, of course, changes after first bite and continues to break down during mastication. And very importantly, the child also learns bolus properties, because it's based on this sensory feedback from the oral cavity that the child can then learn what is a safe bolus to swallow, what bolus is too dry will cause discomfort or choking. And this is all, again, completely learned directly in the cyclical response to the textures that they're exposed to, and then the subsequent ability to adapt that bolus for safer swallow over time. And this is just a visual representation then of the initial chewing behavior, which is initially vertical, one-dimensional chewing linked to what's called munching. And then subsequently, with the emergence of incisors, we have gripping and tearing abilities. So after initially presenting bite-sized pieces or spoon-based feeding, the child can then tear and bite pieces of food off an existing texture, and then subsequently matures towards rotary chewing, which is a much more efficient way of chewing and also enables much more action from the molars to crush food more effectively and to widen up the kinds of textures that can be approached. So from an initial puree lumpy feeding to more complex biphasic or multiphasic textures that need different types of skills, every time a child gets a new texture, they learn a new skill in how to approach that texture and how to safely break it down and swallow it. And although we focus a lot in weaning about the exposure to bitter foods, for example, or the early life taste experiences, much less is known about the appropriate introduction of textures in early life and how that could potentially influence not just food acceptance, but even the development of oral anatomy and the skills needed to chew food safely. And so for the second part, I'll talk a little bit about learning to like, and this is really, as Ranan has highlighted earlier, the role of mere exposure in overcoming those barriers to initial food acceptance, but from a texture standpoint. And the question was asked in the previous talk, why should we move to complementary food? Why would you move to foods that could potentially choke you and that are difficult to consume and where you need a whole new set of skills to consume them? Well, one of the main reasons is the incredibly high energy cost of growth in these young children, equivalent on a calorie for calorie, kilogram per kilogram basis to that of a Tour de France cyclist. So very high energy requirements, and at the same time you have a very small oral cavity with limited chewing capacity and a small stomach. So to get the kinds of nutrients and energy into a child that will sustain the energy cost of growth and still promote healthy growth outcomes, you also have to then develop the equipment to chew that food and nutrient sources in a safe way that can be swallowed and metabolized appropriately. So some quick points about the role of exposure. We've heard from the previous speaker that the recommendations now from SVGen are 4 to 6 months, and there's actually a very important window for texture learning in that 4 to 6 month period. The evidence to date from a wide range of different cohorts worldwide is that texture familiarity will in turn lead to acceptance. Children eat what they like, and they eat what they like and what is familiar to them in terms of their experience with foods. Data from the ALSPAC cohort in the UK has also highlighted that if there is increased familiarity with a texture, it can lead to greater acceptance, and indeed the delay of introduction of textures can have a significant impact in terms of subsequent preferences and dietary patterns. So if you delay the introduction of thicker purees or lumpy foods, it can also lead to difficulties with food fussiness and reduced access or consumption of fruit and vegetables. Fruit and vegetables, of course, are often considered in the context of their sourness or their bitterness, but there's a very significant texture challenge that comes with fruits and vegetables as well in terms of oral processing. And so the estrogen recommendation also aligns with this in terms of not to continue exclusive breastfeeding or puree food consumption beyond 8 months, but to start introducing more challenging textures, and also to use this as an opportunity to encourage more healthy eating behaviours, and indeed in a reciprocal way to support the development of healthy oral anatomy. So our eating behaviours are learned, and this texture experience also makes us better eaters. We become a more efficient chewer, and this is very obvious when you look at the data for solid foods over time. This is data from 30 years ago now, but we can see that over time the number of chewing cycles required and the time needed to chew decreases considerably with the experience of chewing more. But it's important to also highlight that when we talk about basic tastes like bitterness, we're talking about one sensation. When we talk about texture, or more solid textures, we're talking about multiple different types of sensation, and they differ considerably in the kinds of chewing cycles we need for solid foods to get from an initial food through to a bolus that can be safely swallowed. And this is something that we have to understand better in terms of aligning the texture experience with the journey of the eater and their development orally as well. I like to show this study because it's a survey of 3,000 French mothers talking about the cues and the introduction of solid foods to their children. What you can see is that for the most part, most French mothers transition from liquids and purees through to soft, small particle pieces, and then ultimately to harder pieces at around that 6 to sort of 10-month period. And then, as you can see, the prevalence of the harder pieces tends to increase as time goes on further and as chewing efficiency improves. What's also interesting is what are the kind of cues that parents rely on when they're going to make this important transition for their child. And most parents report using age and the number of teeth as the primary drivers to know when to introduce more challenging textures to their child. But is it the case that age and the number of primary teeth are actually driving that ability to chew better? This is other data from my colleagues in France, Carole Tournier again, showing that actually when you look at bolus quality, we can see that children who differ considerably in age, 8 months versus 15 months, produce a very similar bolus. And so age as a marker of the linear relationship between age and chewing efficiency doesn't seem to be very clear. It seems that you can actually have a better chewing efficiency based primarily on your texture exposure and the development of those skills independently of age or even number of teeth. So we see a gradual improvement in chewing efficiency with age, of course, but what's really notable about this is the variation. There's really wide variation in the kinds of chewing efficiency we see there at 18 or 24 months. Some children have very highly evolved chewing efficiency. Other children have the chewing efficiency of a 6 or 8-month-old child. So we're interested in this as a topic, and back in Singapore in my old lab we were interested in, well, how well do age-based recommendations for the texture properties of snacking foods used to support complementary feeding, how well do they align within an age group? And then are they the same also then across categories? And so looking at biscuits, rice extruded snacks and purees, we just wanted to know, are the textures offered to a 7-month-old the same across all biscuits versus the same textures at 9 and 12 or 18 months? And is there a consistency there? Because that would be quite important if parents are basing their choice and consumption behaviour for their children on these recommendations made by manufacturers. And what we were able to show is that there's really no alignment whatsoever between the textures offered specifically at 6 or 7 or 8 or 9 months and then the alignment within that category. So there's very, very wide variation in the textures that are offered at 7 or 8 or 10 months within a category like biscuits or snacks. It's purely based on whatever the manufacturer has indicated. And so there's really a missed opportunity here, because if we can align the textures within these important categories that are used to chew and gnaw, that are used to extend the palate, that are used to encourage the eruption of deciduous teeth in a healthy way, that are used to entrain healthy eating behaviours, if we can align that at those specific key time points along developmental lines, well then there's an opportunity then to optimize that in a way that can actually encourage healthier eating behaviours over time. In the same study, we also showed that parents rely heavily on these label cues in terms of the kinds of foods they will choose for their child. So there really is an opportunity to leverage this and improve the quality of textures offered at these key points of development. Now, for my last few minutes, I'm just going to briefly talk about what is a much broader set of work around understanding eating behaviours in preschool children. So we'll fast forward from the weaning phase and follow children then to the phase of about 4 or 5 years of age. And the reason for that is because a lot of these early life experiences track into later eating behaviors, and then they become consistent over time and linked to things like energy intake and overall transition from potential risk of obesity into obesity proper. One of the ways we can conceptualize this is through this behavioral susceptibility model from Jane Wardle's team in UCL. The idea here is, of course, that if you have a genetic predisposition to obesity and an environment that will facilitate that, one of the ways in which that risk manifests and becomes operational is through heightened appetitive traits, heightened food approach of behaviors. So greater enjoyment of food lowers satiety responsiveness. And one of the areas we were really interested in was how do these manifest then as behaviors when we start to give children test meals or model snacks? How do this risk manifest as actual behavior linked to intake? And so within the Growing Up in Singapore to Healthier Outcomes cohort, we had a group that worked on eating behavior and focused primarily on understanding activities in and around mealtimes and snacking, parental feeding practices, and early life risk, and how this then manifests as differences in energy intake and growth outcomes. Very briefly, the Gusto cohort is about 1,200 parent-child dyads, primarily studied from the point of view of growth outcomes and neurocognitive outcomes. We had the opportunity to study about half of that cohort, looking at mealtimes and snacking behavior with parents. So just an example of one of the results from our many studies in this cohort was that we were able to demonstrate consistently that children that eat at a faster rate will consume considerably more energy within a meal. And this is for appetite-matched children. So at the beginning of the meal, there's no differences in their appetite need state, yet at the same time, children eat considerably more if they eat at a faster rate. And we started to define this as an obesogenic eating style characterized by larger bites, fewer chews per bite, and food would transit the oral cavity at a more rapid pace. And so if that's the case, and if you combine faster eating with softly textured, energy-dense foods, you have a real combination effect where you can have a risk of overconsumption within a meal. And this was work that was led by my postdocs at the time, Kerry McCrickard and Anna Fogel. And we did a lot of work on this on about 500 children. And what we can start to look at then is what are the relative differences in intake among these children and what might be the behaviors linking to that. So if I compare a slower eater to a faster eater, we can see in some cases up to about a 75% increase in energy intake within a single meal. And what's important is when we studied the same children at a later time point, we can see that the same children tended to be the ones that ate faster. And when we relate that then back to their growth outcomes, we can see they also tended to have a more rapid increase in BMI Z-score, but also a more rapid increase in all of the different markers of adiposity, things like skin folds, but also even MRI measured subcutaneous adiposity volumes. So really a risk in terms of specific ethnic groups to have let's say, normal weight BMI, but much more high levels of fat mass and a potential risk in later life. And when we model this then against the wider cohort, we can see that we have what we always expect in terms of early accelerated growth, so children who were born big and then also continue to remain big, but then we were interested also in late accelerated growth, which is children who have maybe a potentially higher risk of developing obesity. What are the behaviors linked to that development of obesity? We focus primarily on obesogenic eating styles, faster eating speeds, eating in the absence of hunger, habitually selecting larger portions, and habitually having more impulsive behavior around food linked to greater energy intakes over time. And so if one of the reasons to learn how to eat, I suppose, is that fundamentally, our anatomy will develop over chronological time. Our teeth will come out, our palates will get bigger, and our ability to use our tongue will improve with age. But the behaviors linked to choice and intake of food, these are all learned, and learned primarily through experiences with food. So there's really an opportunity here to compensate for maybe potential risks by understanding the behaviors linked to the transition to greater obesity risk and weight gain, but also to get a proper start in life in terms of the texture experiential learning that promotes both healthy oral anatomy and healthy eating behaviors in later childhood. So thank you very much.